Hi, my name is Mr. Evangelista, and today we're going to be going over a circular motion problem. Let's read the problem. A coin C of mass 0.005 kilograms is placed on a horizontal disc at a distance of 0.14 meters from the center, as shown above. The disc rotates at a constant rate in a counterclockwise direction as seen from above. The coin does not slip, and the time it takes for the coin to make a complete revolution is 1.5 seconds. So first they want us to draw which way will the acceleration vector point and which way is the velocity vector pointing. Let's draw a quick little free body diagram. Here's the horizontal disc rotating and here's the coin. We have the force of gravity downward, the force normal upward, and the centripetal force in this scenario is the force of friction that keeps the coin going in a circular motion. Now, the centripetal force is the force of friction, and it points towards the center of the circle. That's what centripetal means. Therefore, the centripetal acceleration also points towards the center of the circle. So the centripetal acceleration points towards the center of the circle, as shown below. The velocity vector is tangent to the circle, and so it points this way if the coin is moving in the counterclockwise direction. Remember the examples we did where if you cut the string or if we lifted the hula hoop, then the coin or the ball or the sphere would keep going in a straight direction? Well, that's what we see here. The velocity vector is tangent to the circular motion. B asks, determine the linear speed of the coin. So we need to solve for V. We know that the mass is 0.005, we know the radius is 0.4, and we know the period, capital T, is 1.5 seconds. So we need to find an equation that has those variables in it that allows us to solve for the linear speed of the coin. We know that the v, the linear speed, is equal to the omega angular velocity times the radius. They did not give us the angular velocity omega, so we cannot use this equation. So we're going to have to break it down. I know that omega equals 2 times pi divided by the period t. So if I replace omega with 2 times pi divided by the period, I get this equation, which gives me 2 times pi times r divided by the period gives us the linear velocity. And plugging in numbers, we get 0.59 meters per second. Part C, the rate of the rotation of the disc is gradually increased. The coefficient of static friction between the coin and the disc is 0.5. Determine the linear speed of the coin when it just begins to slip. So slipping happens when we overcome the maximum static friction. So they want to know what linear velocity this happens at. So we need to find the linear speed when we reach the maximum static friction, because that's when slipping occurs. We know that the sum of the forces in the centripetal direction equals mass times the centripetal acceleration. We know that the centripetal acceleration is v squared over r, so let's plug that in. We know that the centripetal force in this case is the force of friction, and we know that the force of friction equals mu times the force normal. So let's plug in mu times force normal for the force of friction. We know that the force of friction is we know that the force normal equals the force of gravity, and if we look at our free body diagram that we drew earlier, the force normal is upward, the force gravity is downward, and they are equal. So we can replace the force normal with the force of gravity, which is just equal to mg. Notice, putting this all together, we get mu times mass times the gravity times the radius equals mass times the velocity squared. Notice the masses cancel out, and we get the velocity is square root of mu times g times r. Plugging in numbers, we get the velocity is 0.84 meters per second. So earlier we saw that the velocity was 0.59 meters per second, and if we keep speeding up the coin, then eventually it will slip, and this new speed we found is when the coin begins to slip at 0.84 meters per second. Lastly, it's saying in the experiment part C were repeated but with a second identical coin glued to the top of the first coin. How would this affect your answer to part C? So we pretty much doubled the mass by gluing another identical coin on there and ignoring the mass of the glue. So we've double the mass, or maybe even more than doubled with the mass of the glue. But you can see from the equation that we had, the mass cancels. So we see that the velocity is just based off of mu, gravity, and the radius. And so doubling the mass will have no effect on the velocity at which it slips.